Welcome everyone to today's video. We're going to start talking about rate laws and integrated rate laws, and specifically here for first order reactions. Okay. So in the previous video, mentioned that we talked about orders of reactions, we talked about how a rate law describes how the rate depends on concentration, okay, and that the exponents in the concentrations give you the order with respect to those specific reactants, and the sum of all those exponents give you the order of the overall reaction, right? So a first order reaction, has a rate law that has, a total exponent of 1. So basically it's going to have one reactant and it's going to have a power of 1, right? And that's a first order reaction, okay? And again, that rate of the reaction, is related with the change in concentration of the reactant with respect to time divided by its stoichiometric coefficient, right? Because again, this rate law, V here is this rate of the reaction, right? Our reaction rate, okay? And that reaction rate is related with the rate of change of reactants or products, right? And so plugging in for the rate of the reaction, okay, we get this differential equation down here, okay, which can be simplified, to this. Okay, and you can potentially write Kr here, A, the stoichiometric coefficient is just a constant, K, R prime is just a constant, so I could call Kr equal to A, Kr prime if you want, right? Okay, and so this is our differential equation. That differential equation, just a first order differential equation, is easily solved, okay, integrated out, and we're integrating from some time 0 to some time t, where we have an initial concentration A naught to some final concentration A. And we do that integral, we get ln of A over A naught minus kt, okay, or equals negative kt, sorry. Or you can write that as concentration of A equals concentration of A naught times e to the minus r kt, And then this form also has been, you can also write it as ln concentration of A equals minus kt plus ln concentration of A naught, Where then this is, your equation for a straight line, y equals mx plus b. B is your y-intercept, and m is the slope, where the slope is minus k. And so a plot of that concentration versus time, gives you this exponential decay, where the decay is faster, the larger the rate constant, Which makes sense, The larger your rate constant, the faster the rate, the more quickly you lose concentration, So that decay is much more rapid as k gets larger, No surprise there. And so how can we use this information in lab, Well, often in lab, what you can do is you can measure the concentration of some substance as a function of time, Let's say you're using absorption, You're doing UV vis, The peak height of that spectrum is related to the concentration of your substance, So you measure the peak height as a function of time, and you get concentration as a function of time, for example, You can measure things like currents for ions, all sorts of things, vibrational spectra, lots of different things you can use to measure in lab to get the concentration of a substance as a function of time, okay? And so once you have this concentration versus time data, the question is what can you do with it to determine if it's first order, Well, might I plot, and how can I get out the rate constant, Well, if you have a first order reaction, again, if you were to plot the natural log of A versus time, you'd get that straight line, You'd get, if I made some type of plot here, of natural log of concentration of A versus time, I would get some sort of straight line with a negative slope, Okay. And that slope here, is just equal to the minus the rate constant of the reaction, okay? And so doing that right in lab then would let you know, hey, this is a first order reaction, if that's a straight line, right? If it's not a straight line, if we don't get a straight line, it's not first order, okay, and a reaction some other order with respect to A. Okay. Another way you can identify if something's a first order reaction is by looking at the half-life of the reaction, right? The half-life is the time it takes for the reactant to reduce by half of its initial concentration, right? And so if we use that, right, that means for our integrated rate equation, right, if I want to solve for the half-life, right, the half-life is related when the concentration is 1/2 the initial concentration. So I plug all that in, solve, and you get this equation down here. Okay? Note that this is concentration independent. This is only true for first order reactions. For other higher order reactions, right, there will be some concentration dependence, right? And you can think about this, right? For 0th order reactions, right, the rate of the reaction does not depend on the concentration. So the more stuff you have, the longer it takes to reduce its concentration by half, right? So if I have 100 moles, it's going to take, and I reduce 1 mole per minute, no matter how many moles I have, right? It's going to take a lot more time to get from 100 to 50 moles than if I had 10 moles, right? And going from 10 to 5, right? So reducing that concentration by half, the time it takes depends on what the initial concentration is for a 0th order reaction, okay? But first order reaction, right, you increase the concentration linearly, right? Right, and that linear increase in concentration corresponds to a linear increase in reaction rate, okay? Right, and so because of that, the time it takes to reduce the concentration by half is the same no matter how much you have, right? But for second order, right, as you linearly increase the concentration of your reaction, right, your reaction rate will go up by a power of 2, right? Because it's concentration squared, okay? So you're going to get faster and faster and faster rates the more and more stuff you have, right? Which means it should take less time as your concentration gets larger to reduce that concentration by half, okay? And then that same thing's true for even higher orders, third orders, fourth orders, and stuff like that. So it's only first orders as this unique thing where the half-life is independent of the initial concentration. Okay. And that's true for all first orders, right? And then this is used often, for things like radioactive decay, which then can give us carbon dating and all sorts of other things like that, right? And so first order reactions occur often, right? Especially in nuclear chemistry, and they're very useful, this property, in order to be able to predict things, again, like the lifetime of something, how long something's been around, and stuff like that, because of the fact that half-life that we can measure and know for any compound, right? For nuclear reaction, it has this half-life, right? I can know that, and it doesn't matter what the concentration initially was, and then I can just look at what is the percent change in concentration, right, which doesn't depend on the initial, right, and that can get me how long something has been around, okay?